Assalamualaikum and good morning, everyone. So we're done with topic 6, electrochemistry. Now we're moving on to the next topic, topic 7, Equilibria, or as you all know it as equilibrium. This still comes under physical chemistry, so you should be expecting to deal with numbers and calculations. The first section that we are going to look at is reversible reaction and equilibrium. Just to briefly introduce to you the idea of reversible reaction, which I think you should already know by now. And that is mentioned under the learning objectives. To understand the term reversible reaction, also to understand the term dynamic equilibrium, in terms of the rate of reaction, and also to understand the need for a closed system to be to get or to establish dynamic equilibrium. Okay. First, irreversible reaction is a reaction that can only take place in one direction. That means once you have used up all your reactants to form your products, the reaction will stop. Whereas reversible reaction is a reaction that can take place in both directions. So we have a forward reaction or a backward reaction, sometimes called reversed reaction. So once your reactants are forming products, the products can start to reform the reactants because this is the kind of reaction that happens in both directions. All reversible reactions will reach a dynamic equilibrium state. I will explain to you shortly what dynamic equilibrium means. So this is just some elaboration of what I've already spoke about earlier on. A reversible reaction is shown by the symbol, we call this two half arrows, okay? The reason why it's called two half arrows is because you have half an arrow going forward and another half an arrow going backwards or in the reverse direction. So whenever you see this symbol, that means the reaction is reversible. Here is an example to show you a system of a reversible reaction. It is the conversion of hydrated copper sulfate to anhydrous copper sulfate. So I will just write down a reversible reaction, maybe a different color, green. Okay, so we've got your hydrated copper sulfate. And then you can separate them into anhydrous copper sulfate plus 5H2O. So the water molecule is no longer associated with the crystal, okay? Please take note that even though we've got the copper sulfate to be hydrated, it is still a solid. It's not the aqueous form, right? But I will not talk much about that. I named this hydrated copper 2 sulfate. Now you're already familiar with what that number 2 indicates in the bracket. And this is anhydrous when you have separated the water molecule from the copper sulfate. Okay. And this system has two reactions going on at the same time. Okay. So it can be broken down into forward reaction, which is just the one from left to right. Now, if you are writing down the equation on its own, you would use a full single arrow. And the backward reaction, or sometimes called the reverse reaction, also called reverse, is when your anhydrous copper sulfate recombine with the 5 water molecules to form your reactant. Okay, so if you know how to go from the reversible reaction into its individual reaction, then you should also be able to go in reverse, combining two equations or two reactions to achieve a reversible reaction. Okay, so there's a text here saying the diagram shows an example of a forward and backward reaction that can be written as one equation using two half arrows. So this is an important symbol to show. The two half arrows is an important symbol to show that this equation happens reversibly. Okay, so if you want to copy this down, you can pause the video. Next, I want to talk about dynamic equilibrium. So there are three features of dynamic equilibrium. The word dynamic means both forward reaction and the reverse reactions are happening simultaneously. Okay, if you are familiar with the word dynamic in our everyday use, you would know that dynamic is ever-changing, moving, constantly moving. Okay, so what are the features or the criteria of a system to be in a dynamic equilibrium? First, the forward and the backward reactions are occurring at equal rates. So that means how fast your forward reaction is going is the same rate as your reverse reaction is going. Okay, no one is faster than the other in dynamic equilibrium. Okay, once they reach dynamic equilibrium, they move at the same rate. One thing, the most common misconception of a dynamic equilibrium is that students think that the concentrations of reactants is equal to the concentration of products at dynamic equilibrium. That means that if I have 50 mole per dm cube of products, then I should also have 50 mole per dm cube of reactants because the rate is the same. Now that is not true. Rate may be the same, but the amount, the concentrations are not, and that is fine. And lastly, it requires a closed system. That means your container, especially for gas reactions involving gas molecules, you want your container to be closed so that your gas cannot escape. Okay, especially gaseous reactants and products. So, but we try to be safe. Even if we're using liquid, we do not want it to be exposed to the air. We want to make sure that even at liquid form, they occur in a closed system, because some liquid may be volatile. They convert into gas readily. Okay, so your gaseous reactants and products cannot escape from the mixture, the reaction mixture. That means everything, your reactants and your products, are mixed in the system or in the mixture. Moving on. Here is an example of a dynamic equilibrium. This is an example of a reversible reaction. In the forward reaction, you can see that the hydrogen combined with the iodine to form a molecule of hydrogen iodide, right? That's the forward reaction. The reverse reaction is the hydrogen iodide breaks to reform the reactants. So hydrogen iodide will break down into hydrogen and iodine molecules, right? Sometimes we say the word reforming the reactants, okay? The products react together. In this case, there's there's only one product, okay? But the key word is reforming the reactants at the same time as the reactants forming products. So that's the criteria of a dynamic equilibrium. Forward rate equals to backward rate. Okay, so that's the mention of same rate. This is a graph of a concentration time graph. I am sure that you have seen a concentration time graph before. It tells you how much concentration you have as the reaction proceeds. The first graph that is showing you is, if you look at the equation, hydrogen and iodine is your reactants. And hydrogen iodide is your product. So we want to look at the start of the reaction here, because your x-axis is time and concentration can be seen as the amount, how much you have of the reactants or the products as the reaction proceeds. Okay, so over time, you can see that your product, which is the green line, is increasing. That means you start from zero product, nothing, and then as the reaction proceeds, you start increasing, producing more product until you reach what looks like a constant line. Okay, whereas your reactants, I think you are familiar with the concentration time graph of a reactants as well. Initially, you have some amount of reactants, okay? And over time, as your reactants combine to produce product, you have your reactants decreasing until it reaches again a constant line, a flat line. Now, one thing to note about dynamic equilibrium is that your reactants will never go to zero. Your reactants will never be used up. Why? Because even though you're using your reactants, hydrogen and iodine, to produce hydrogen iodide, remember hydrogen iodide can also break up to produce the reactants. Okay, and once it reaches the flat, the stable, the constant line, it just means that equilibrium, dynamic equilibrium has been reached, and it doesn't mean that the reaction has stopped. They are now still forward reaction occurring, reverse reaction occurring. The concentration stays constant because they are both happening at the same rate. So you can continue with your dynamic equilibrium as long as you have a closed system. They will continue to happen simultaneously. Forward, reverse, forward, reverse, forward, reverse. Okay, so I want you to label in your graph before I let you copy down the text in the box. Okay, so you can see that looks like a straight line for the products, and that's for the reactants. Okay, now ideally they should be the same, but I'm going to follow the product. Okay, so I can see that the start of the equilibrium is here. That means equilibrium has been reached. When the products are decreasing and the reactants are increasing, this is just happening in a normal reaction, okay? But the equilibrium is reached when the concentration of the products and the concentration of the reactants are constant. Try to avoid using the word same, because same means if you're saying that the concentration of hydrogen iodide and the concentration of the products and the reactants are same, then they should land on the same value. For example, like this, if I were to redraw the graph of a reactance. Okay, so we say that concentration of products and reactants remain constant. That means it is not changing even though reaction is still happening. Okay, avoid using the term same. Another thing that I want you to add to your notes is that the concentration of your reactants doesn't fall to 0 as there are always reactants left. Now, if you have your concentration falling down to 0, that means there's no more reactants left. The reaction should stop. But in a dynamic equilibrium, the reaction continues, the forward reverse continues at the same rate. Okay, so please copy down the explanation in the box. So this is a scenario where the reaction begins with only your reactants present. That's why you have reactants starting from the top. Over time, your reactants will decrease, but it reaches a certain constant amount. It's not 0. As the reaction proceeds towards equilibrium, the concentrations of your products will decrease while the concentration of your, the concentration of your reactants will decrease, whereas the concentration of your products gradually increases. When the curve levels out and the concentration all become constant, equilibrium has been reached. Now, I forgot to mention that if the equilibrium has been reached for the products, that means it must also has been reached by the reactants as well at the same time, because we are looking at the vertical line. That's where your X is. So it's not correct to say product has reached equilibrium, but reactants haven't. Both of them must reach the equilibrium stage at the same time at a certain concentration. So after equilibrium, just to remind yourself that after this time, reactions are still occurring, both forward. Reactions are still occurring. Okay, right. So if you want to copy this down, please pause the video here. And if you cannot see the details on the graph, you can pause the video here. Please pause. Moving on. Next is for a different scenario. It's still the same system, but this time you have some products to begin with. Okay, 0 reactants. Notice that the graph of the reactant is coming from 0, and the products you start at some number, right? So what happens? Same thing. The products will first start to reform the reactants. Once you have reactants, then only the forward reaction happens. The reverse reaction is happening until they reach a point where the concentration becomes constant. I would just, well, it should be a straight line. Okay, so that's the point where equilibrium is reached for both of them. Okay, I would just label this as my products, and this is my reactants. So in a reversible reaction, in a dynamic equilibrium, you don't necessarily have to start with reactants. You can always start with product, but of course, you need some time to produce reactants so that the forward reaction happens, okay? So imagine if I just throw in my hydrogen iodide into a vessel, a closed container. What happens is that first my hydrogen iodide will slowly break itself down into hydrogen and iodine. Once I have some hydrogen and iodine, which are my reactants, then I can get the forward reaction to go. At the same time, my reverse reaction is also going on until I reach a point where my rate of forward is equal to the rate of backwards or reverse reaction. And at that point, my concentration is also constant if you look at the graph. Okay, so if you want to copy this down, you can pause the video here now. Next, we are going to look at the Le Chatelier's principle. I am sure that you have heard of the Le Chatelier's principle already, so I will go through this quickly, but at the same time, I also don't want you to not understand it. It is important for you to understand your Le Chatelier's principle because you need this for this topic, right? You have to define Le Chatelier's principle, and then you have to use Le Chatelier's principle to deduce qualitatively the effects of changing temperature, concentration, pressure, or adding catalyst to a system at equilibrium. So you want to know what Le Chatelier's principle is and what it does when you change the external conditions of your reversible reactions. Le Chatelier's principle states that if there is an external change made to an equilibrium, the equilibrium will adjust so as to oppose or to cancel out the change being brought, and then it reforms a new equilibrium. Okay. We use Le Chatelier's principle to work out how changing conditions can affect the position of equilibrium. So I'm sure you all have come across this term, position of equilibrium, shifted to the left, shifted to the right. But what does it actually mean? The position of the equilibrium actually can tell us the relative amount of the products or the reactants that we have in an equilibrium mixture. Okay, the amount can be moles, can be concentration, right? So when we say the position of the equilibrium is shifted to the left, so if I have A to B, okay, where A is my reactant and B is my product, and that my equilibrium is shifted to the left, that means I have more B. Sorry, that's shifted to the right. That's right. Okay. Shifted to the left means that, okay? That means I have more A than I have B in my equilibrium mixture, okay? The word relative means you have to compare how much more one person is than the other. The most important thing is no one, A or B, is ever zero in an equilibrium. If it's zero, that means it's no longer equilibrium. It's probably an irreversible reaction, okay? What if it's the other way that I was talking about just now earlier on? The position of the equilibrium is now to the right. That means I have more B than I have A in terms of amount. Okay, that means higher proportion of products than reactants. So that's what position of equilibrium tells us. It tells us the composition of the equilibrium mixture. That means the contents at equilibrium. Sometimes we use the word favoring forward reaction. That's the same as shifting the reaction to the right. Favoring backward reaction means shifting the equilibrium to the left. So just remember that when you have A and B, A to B, A will always be your reactants, B will always be your products, even if we're talking about the reverse reaction. Because if you think about it, when we look at the reverse reaction, B is our reactant, right? And A is our product. But as a conventional way of labeling things so that we don't get confused, we always call anything to the left as your reactants and anything to the right as your products, regardless of which direction we are going to look at. Moving on. There are a few factors that can affect the position of equilibrium, okay, whether it shifts to the left or whether it shifts to the right. And the factors are concentration, pressure, and temperature. There's the fourth factor that does not affect the position of the equilibrium is the catalyst. Now we're going to look at what happens if we change the concentration of a reactant or product. How is our equilibrium going to adjust, and what does Le Chatelier's principle role in this changing of the condition? Okay, so I have a system here. It's a reversible reaction who is currently at the moment under dynamic equilibrium. So that means my forward reaction, which is shown going from left to right, is happening at the same rate as my backward reaction, which is shown from right to left. Okay, so this reaction is showing the reaction between ethanoic acid and ethanol. So this is a familiar reaction for you. It's ester production. Forward, we call it esterification. And backwards, I don't know if you still remember this, but we call it hydrolysis. We are breaking up the esters into its starting materials, acid and alcohol. Okay, right. So what happens if we change the concentration? Okay, so whenever you want to talk about the effect, you must include 2 points. Okay, the first one, which side it favors? Where is the position of the equilibrium shifted to? Okay, and the second point is, what is the effect to oppose the change? Okay, right. Now, this is where your Le Chatelier's principle come in. Le Chatelier's principle said that if my dynamic equilibrium is changed, my system will do the opposite to cancel out the change. Okay, right. First scenario is what happens if we increase the concentration of the reactant. Okay, so here we are using specifically ethanol. Okay, what happens if we increase the ethanol? Le Chatelier's principle would say, okay, you increase the ethanol, now I want to decrease my ethanol. How do you decrease ethanol? Is by reacting it with ethanoic acid. That means you are favoring the forward reaction. By favoring the forward reaction, you are using up ethanol. So whatever increase or whatever extra is added is now cancelled out. Okay? Explanation. Equilibrium will shift to the right. That means forward reaction is being favored. The reason why is because to reduce the concentration of ethanol, which is the one that is being added extra, to reduce this extra, the ethanol needs to react with carboxylic acid to form ethyl ethanoate and water. Okay. Next, I hope you can follow that, and I hope that is not too different from what you have learned already in O-level. What if this time we want to increase the concentration of products? So we are now in a different scenario, okay? We've already dealt with increasing ethanol just now. Next is we want to try to increase water, okay? So look at here, water is increased. So what Le Chateliers is saying is that we need to decrease water. Okay, how do we decrease water? By reacting water with ethyl ethanoate. So we are favoring the reverse reaction, or we say that the equilibrium is now shifted to the left. Okay, explanation. Equilibrium shifts to the left. That's what I just said. It favors the backward reaction. So you can choose either one, whether you choose to talk about the shift of the reaction, or the forward and backward reaction. Okay, it's the same thing. The reason why the equilibrium shifts to the left is because we want to reduce the concentration of water. If you want to reduce water, you make sure that water is reacted. Water reacts with ethyl ethanoate to produce ethanoic acid and ethanol. So this is a reform. Water reacts with ethyl ethanoate, which is your ester, to reform your reactants. Okay, moving on. What if now we do decreasing? Okay. What happens when ethanoic acid is decreased or removed? That means this concentration goes down. Le Chatelier's principle said that, well, if my concentration is going down, I need to bring it back up. What's a way to increase the concentration of ethanoic acid is by producing it. So that means ethyl ethanoate needs to react with water to produce more ethanoic acid and ethanol. Okay, you don't want your concentration to decrease and then you favor the forward, because what happens here is that you are using up your ethanoic acid. Now you already have less. You don't want to use up your ethanoic acid. Right? So what happens is, I repeat, you bring down, you decrease, you remove your ethanoic acid. You want to reform more. You let your ethyl ethanoate react with water. So this means we are favoring the reaction to the left. We are shifting the equilibrium to the left so as to produce more ethanoic acid. Okay, and then equilibrium will try to reach a new one on its own. We don't have to worry about that. Okay. Explanation: when ethanoic acid is removed, equilibrium shifts to the left, which is what I just said. It's the same way as saying favoring backward direction. To increase the concentration of, oh, it's not ethanol. It should be to increase the concentration of ethanoic acid. We're not talking about ethanol here. We want our ester to react with water. Okay. Next, decrease the concentration of ethyl ethanoate. What happens if we remove ethyl ethanoate? Le Chatelier's principle said that, well, if we remove ethyl ethanoate, we need to produce more. And how do we produce ethyl ethanoate? Is by favoring the forward reaction. So ethanoic acid will react with ethanol to produce more ethyl ethanoate so that we can cancel out or we can overcome the change being made. That's the idea of Le Chatelier's principle. Okay, so in explanation, equilibrium shifts to the right, which is favoring the forward reaction. The reason for this shift is to increase the concentration of the ethyl ethanoate that was being removed earlier on. Okay. All right, I hope you can follow that. So the exam tips is, when answering in the exam, about the effect of changing the concentration, please include these two things that I just mentioned just now. Which site or which reaction is being favored, and then the effect of shifting this position. Now, what does favoring this reaction doing? Okay, so usually most of the time it is doing to oppose or to cancel out the changes to the condition, which is following the Chateliers principle. Okay, example 1. Let's do a quick example. What is observed when the concentration of hydroxide ions is increased? So that means we are increasing hydroxide ions. Chateliers principle said that, well, if my hydroxide ions is high, I need to reduce it. And the only way to reduce my hydroxide ions is favoring the forward reaction. Okay, so to answer this, the forward reaction is being favored. I'll let you copy down the text after this, but I'll just give you the answer verbally and see if you can follow my answer. Okay, so what happens? The forward reaction will be favored. This means that to reduce the concentration of the hydroxide ions, it needs to react with the iodine to produce more products. Okay, that's the only way of reducing the OH minus ions. Part B. What happens if we add hydrogen ions? Now, do you notice that in this system of reaction iodine with hydroxide ion to form iodide, IO minus ion and water, there is no H plus in this equilibrium mixture? Okay, sometimes adding stuff that is not in this equilibrium mixture will have no effect. However, this is H plus. Even though H plus is not in the equation, but H plus actually indirectly affect the equilibrium. What does H plus react with? It reacts with the hydroxide ions. So that means if you add H plus, it will react with OH minus. Okay, there are two ways of seeing this. OH minus reacting with H plus means OH minus is being used up. So that indicates a decrease in hydroxide ion. And what does the Chatelier principle say? If my hydroxide ion is reduced, then I need to produce more hydroxide ion. And the only way to produce hydroxide ion is by favoring the reverse reaction. My products need to combine with each other to reform hydroxide ions. Okay, that's one way of seeing it. Second way of seeing this is, as I said, I'm adding H plus and I've got OH minus in the mixture. That means I am forming H2O. Adding H plus is indirectly affecting the equilibrium mixture because I am now increasing my H2O. If I want to increase my H2O, what does Le Chatelier said? Well, sorry, if my H2O is increased, Le Chatelier said, well, you now have to reduce your H2O, decrease your H2O. So decreasing H2O means you have to use up H2O with the other products to reform your reactants. Can you see that the effect is the same? You are essentially favoring the reverse reaction. You are shifting the equilibrium to the left. The only difference is in the reasoning, but the effect is the same. Okay, so how do you answer this? I've prepared the answer for you. So please read again as you copy them down. Make sure you can understand them. If there's any typo error or any word that contradicts the explanation, please let me know. Okay, so you can pause this video here so I can move on to the next one. The next one, we're going to look at the effect of pressure on equilibrium. When we talk about pressure, we only apply this to gaseous reactants and gaseous products. Okay, so please make sure that pressure will only affect an equilibrium system that has gaseous reactants and gaseous products. Pressure does not have any effect on solid and liquids. The general idea is that generally, when you increase the pressure, the reaction will go towards the smaller number of molecules. When you decrease the pressure, the equilibrium will go towards the side with the bigger number of molecules. Okay, now let's see. First example is the reaction on the left, which is nitrogen plus 3 moles of hydrogen to form 2 moles of ammonia. I would just label or count the number of molecules in total. So we've got 4 moles on the left and 2 moles on the right. Okay, before I go on to the explanation, what happens when I increase the pressure? If I increase the pressure, Le Chatelier would want me to reduce it, right? Because it has to do the opposite. So how do I reduce the pressure of a reaction is by moving towards the smaller number, okay? So that I have less molecules, therefore lower pressure. That means increasing the pressure in this case would favor the forward reaction because I am going towards the side with smaller number of molecules, right? In explanation, equilibrium shifts to the right, that is the forward reaction, as there are fewer gas molecules on the right. So that's what I just said. If you want to be more specific, the pressure is reduced by using up the site with the big number of molecules. That is the nitrogen and the hydrogen, so that you produce smaller number of molecules. Now you may be asking, why is that smaller number of molecules will cause your pressure to be lower? The reason is because pressure is defined as the number of times your molecules, gas molecules, collide with the walls of your container. So if you have less number of molecules, less collision with the walls of the container, therefore lower pressure. So this is what you have already learned in topic 4. Looking at the equation on the right, we have got a reaction between carbon monoxide and 2 moles of hydrogen. In total, there is 3 moles. And in the product, there is 2 molecules, okay, if you would like to see it that way. What happens when we decrease the pressure? We are now lowering the pressure. Le Chatelier would want the equilibrium to increase the pressure just to offset this change. Okay, so how do we increase pressure? We increase pressure by favoring our equilibrium towards the side with the bigger number of molecules. Okay, in explanation, equilibrium shifts to the left. So that's what I just showed you, as there are more gas molecules on the right. It shouldn't be right. It should be left. Okay, so that is a typo. Luckily, I read. As there are more gas molecules on the left. The pressure is increased by producing more reactants, carbon monoxide and hydrogen. Okay, for pressure, it's quite easy as long as you get the idea. Increasing pressure, you go to the site with lower number of molecules. Decreasing pressure, you go to the site with the higher number of molecules. Next is, what if the number of molecules is the same on both sides? On the left, we've got 2 moles. On the right, we've also got 2 moles. Essentially, you are just increasing the rate of reaction of forward and the reverse. You're increasing by the same amount. Therefore, the change cancel out. There is no effect on the position of the equilibrium. But increasing pressure, we know that it has an effect on the rate of reaction, which is something that we haven't covered yet, but we'll cover in the next topic, okay? So since they are favoring forward, favoring backwards, we just say that there is no net change. There's no effect on the position of the equilibrium. Moving on to the next change in condition is the effect of temperature on equilibrium. Okay, so temperature is a little bit tricky because of the endothermic and exothermic, but once you get the hang of it, you should be able to work it out. Now, just a reminder, if you increase the temperature of something, of your mixture or your system, the endothermic reaction will be favored. Why? Because endothermic likes to take in heat. Whereas if you reduce the temperature, you lower the temperature, the exothermic reaction is being favored. Okay, so you have to look at your reversible reaction. You have to look at your enthalpy change, delta H. What's the sign? Is it positive or negative? And then only we can talk about the effect. First reaction, that first system that we're going to look at, okay? The reaction between nitrogen and hydrogen to produce ammonia, the formation of ammonia is actually, it has a delta H of -92. What this indicates is that the forward reaction is -92 kilojoules per mole. As you know, that's exothermic. And reverse reaction is the opposite sign, but of the same value. So we say that for a dynamic equilibrium system of the formation of ammonia, the forward reaction is exothermic and the reverse reaction is endothermic. So I'll just write it as exo and endo. Okay, does it matter? Yes, it matters because it will affect your Le Chateliers principle. Is it favoring the forward or is it favoring the reverse? Okay, so delta H that is given to you in papers, in exam, in textbook is always referring to the forward reaction. If you want to know the delta H for the reverse reaction, it's the same value but the opposite sign. Okay, increase in pressure, decrease in pressure. So that's obviously a typo that I forgot to change. It's a copy and paste. Increase in temperature or decrease in temperature, right? So let's see, before we even look at the explanation, what happens when we increase the temperature? Now, if we increase the temperature, Le Chatelier principle would say, now we have to reduce the temperature. And how do we reduce the temperature? We take in the extra heat, take in the energy. So which reaction is the one that takes in energy? It's the endothermic reaction. So that's why endothermic reaction is being favored if you increase temperature. And endothermic reaction happens to be the reverse reaction in the system. All right, so we are favoring the reverse reaction, which is endothermic. That means your extra heat, extra temperature is being taken in by the endothermic reaction. Explanation: increase in temperature favors the endothermic reaction. We've talked about that. The equilibrium shifts to the left. Yes, this is because endothermic reaction takes in heat, therefore it reduces the temperature. Okay, take in heat or absorb is the same thing. Next, what happens if we decrease the temperature instead? If we decrease the temperature, Le Chatelier's principle say that we have to increase the temperature. We have to produce heat. We have to give out heat. And this is the characteristic of an exothermic reaction. What exothermic reaction does is that it gives out heat. An exothermic reaction in this system is the forward reaction. So the forward reaction will be favored. Your temperature, heat will be given out. So now your temperature will restore or return back to normal after there's a change to it. Okay, because we say that we decrease the temperature, Le Chatelier say, no, we have to increase it back. And only exothermic can do that by releasing heat. Decrease in temperature favors the exothermic reaction. That's correct. Exothermic reaction is to the right, yes. And what exothermic reaction is that does that it releases heat so that the temperature increases back to normal. Okay, I hope you can follow that. We'll move on to the exercise, okay? Explain the effect of increasing temperature on this reaction. So now we have a system of hydrogen reacting with carbon dioxide to form water and carbon monoxide. And the enthalpy change, the delta H is positive, which means forward is positive 41.2, oops, 41.2. So that's forward endo. And the reverse is negative 41.2, reverse exo. Right? Explain the effect of increasing temperature. So again, we increase temperature. Le Chatelier said, no, reduce. We have to lower down our temperature. And to lower down our temperature, we need to favor the endothermic reaction so that it absorbs or it takes in the heat, the extra heat. Okay, so what happens? Increased temperature, endothermic reaction will be favored, and that is your forward reaction. Your equilibrium shifts to the right. Additional energy, additional heat will be taken in or absorbed by the endothermic reaction. Okay, so first we talk about the shift. How will our equilibrium be shifted? Increase in temperature, well, I don't want to confuse you with the color. So we say that increase in temperature favors the endothermic reaction. Okay, so this is the same as saying forward reaction is favored, or we say that the equilibrium shifts to the right. Okay, so sometimes it is worth mentioning because the question will ask you what is the effect of increasing temperature does on the equilibrium. So mention that the equilibrium shifts to the right. The reason for this is that additional or extra heat energy will be absorbed, or you can use the word taken in, used up by the endothermic reaction. In this case, our endothermic reaction is when hydrogen reacts with carbon dioxide, okay? Forward reaction. Okay, if you want to copy that down, you can pause. I'm going to move on. The next question, increasing the temperature increases the amount of CO2 at constant pressure. Is this reaction exothermic or endothermic? Explain your answer. So now we're going to do the reverse. Okay, they tell us the effect of increasing the temperature, but we don't know what our enthalpy change is. Okay, we can work it out. It says the keyword here is that increasing temperature increases the amount of CO2. T increases, CO2 increases. And if you can see, your CO2 is in your product. That means increasing temperature has favored the production of CO2. Increasing temperature has influence in the production of more CO2 in the system. That means the forward reaction must have been endothermic. Okay, because only endothermic reaction will be favored when there is a temperature increase, because what it does is that the endothermic reaction will take in, will absorb this additional heat. So how do we explain this? Increasing temperature will result in the reaction absorbing this heat and caused a shift to the right, which is the product side. In bracket, we know this because more CO2 is formed. Therefore, forward reaction must be endothermic. Endothermic. Okay, so delta H is positive. We don't know what the value is. Okay. If you want to copy this down, please pause the video here, and then you can copy it down. Next, I'm going to talk about the effect of catalyst on equilibrium. Now, when we add catalyst to the equilibrium, if we had an equilibrium, for example, I'm just going to use a simple system A to B, and assuming that they are in dynamic equilibrium, what the catalyst does is that it will favor both the forward and the reverse reaction. Again, this scenario looks familiar. If you favor both forward and reverse reaction by the same amount, they will cancel out and effectively no change to your equilibrium. So a catalyst has no effect on the position of the equilibrium. What catalyst does is that it speeds up the rate of reaction of the both forward and backward reactions so that equilibrium is achieved more quickly. But in terms of the position, and earlier on when I said when we use the word position means it's the content or the amount, okay? So the amount or the content of your reactants and products will not be changed if you add catalysts. It will just speed up both of your reaction. So to summarize, okay, what Le Chatelier's principle is that when you increase temperature, the system will try to reduce it by favoring endothermic side. If you increase the pressure, the equilibrium will reduce the pressure by moving towards the side with fewer gas molecules. And if you increase the reactants, the concentration of the reactants, the system will try to reduce it by reacting it. So that means it's the forward reaction, okay? Next, I am just going to cover the first part of equilibrium constants so that in the next lesson, we can get on with the calculation. Equilibrium constant is a number. that is constant for a particular system. That means if you change the concentration, the constant will not change. If you change the pressure, the constant will not change. Adding catalyst will not have effect on this number as well. There's only one factor that will change the number or the size of your equilibrium constants, and that is change in temperature. Next learning objective is to deduce the expressions for equilibrium constants in terms of concentration. There are two types of equilibrium constants. First is the concentration in terms of concentration, and the second one is in terms of pressure. We'll deal with the one in terms of concentration first, and the symbol for that is Kc. Deduce expressions for equilibrium constant. Oh, okay, so that's Kp, that's for later. Okay, so as I said just now, there are two forms of the constant, Kc or Kp. If we're using Kc, we should be talking about the concentration. Kc applies to liquid and gas only, not for solid, because, well, solid doesn't have a concentration, so we leave solid out. Kp is equilibrium constant based on partial pressure. Okay, I will talk about partial pressure later on. And because we're talking about pressure, it only applies to gaseous reactants and products. No liquid, no solid, no aqueous. And as I have mentioned just now, values of Kc and Kp are affected by temperature only. So students think that because Kc and Kp are numbers, so if we increase the concentration of either your reactant or products, this number will also change. No, only temperature can change the number. Only temperature can change the constant. Okay, so we're going to look at what is this equilibrium constant. We focus on Kc first, okay? It's not easy to define equilibrium constant, but I feel like it's easier to write down the expression, okay? Just a reminder again that solids are ignored in this equilibrium expressions because solid doesn't have a concentration, right? If we have a general equation of reactant A reacting with reactant B to produce product C and product D. This letters M, N, P, Q, those are the mole ratios, or we call it stoichiometric numbers, okay? To write down Kc, Kc is an expression that has got the numerator and the denominator. So on the top or the above expression, the numerator, we have the concentration of products. For this topic, and from here on, concentration is written as square bracket, okay? So my products are C and D. So I will write it as the expression of concentration of products, C and D. And then the mole ratio or the stoichiometric number is written as the power, okay? Concentration of C raised to the power of P, which is the mole ratio. Concentration of D raised to the power of Q, okay? Over concentration of reactants, concentration written as square bracket A, raised to the power of M, and concentration of B raised to the power of N. So we always have the products, concentration of products raised to the power of its stoichiometric ratio over the concentration of reactants. Now, concentration would have the unit mole per dm cube. This is important, okay? So if we're talking about one concentration, the power is mole per dm cube. Now, what is the unit of Kc? The units of Kc has to be worked out based on each individual expression. It depends on the system. So Kp will have several units depending on which reaction, which reversible system that we are looking at, right? I will show you when we look at the example after this. So the explanations are given here, okay? What M and P and Q are, what the square bracket stands for, and AB is your reactants, CD is your products. Next, what does the number of Kc tell us? So that's what the magnitude, okay? Magnitude is like size or number. The magnitude of Kc as well as Kp actually can tell us the position of the equilibrium. That is all. It cannot tell us the rate of reaction. Why? If you look at my Kc, and I have written it as concentration of products over the concentration of reactants. Although strictly speaking, I should be looking at raising them to the power of its stoichiometric number. Okay, but generally, Kc is proportional to concentration of products over concentration of reactants. So if you just imagine, if my Kc is, if my products are big than my reactants, my Kc would be a big number. Yeah, just like you have, just some number. If we just take like 20,000 over 50, the top number is bigger than the bottom number. So I know that X will be something big, right? So that is the same case here. If the top number, my products are big, my Kc would be big. At least it's bigger than 1 since it's a fraction. If it's the other way around, my bottom number is bigger, I know X would be a small number, a smaller number, okay? So this Kc can actually tell us about the position of our equilibrium. Do we have more products or do we have more reactants, right? So if our Kc is small, that means, okay, if we look here, Kc is a small number, so my reactant must be big. Yeah, my denominator has to be big. That means my equilibrium is shifting to the left, shifting towards the reactant side. If my Kc is big, my products are bigger than my reactants. My equilibrium is shifted to the side of the product or favoring the forward reaction or shifted to the right. So that's just the qualitative measure of Kc. Later on, you will work out the quantitative value for Kc of different reaction. Okay, last one before we go, we're going to look at the example and how to write the Kp expression as well as working out the units. First example that we are going to look at is the reaction, the system of the production of ammonia. Okay, so Kp is equals to product, the concentration of product. So first thing that we should do is check that everything is either liquid or gas. So they're all gas. So everything will appear on the Kp expression. So I start with my products. NH3 gas, the concentration of my products, you must include, you must include the square bracket. If you don't write down the square bracket, it doesn't mean anything. Square bracket indicates it is the concentration of NH3 raised to the power of 2 because that is the mole ratio. Okay, that's the only product that I have over reactants. Nitrogen gas, since it's 1 mole, it's to the power of 1, times by the concentration of hydrogen gas raised to the power of 3. Again, for the same reason, that 3 is the mole ratio. Next. Okay, so that's my Kepler expression done. It's quite easy, right? So I make it a habit to include the state symbols so that I know they're all liquid and gases. There's no solid in there. Next is working out the units. Some of you may be really good at this if you've learned how to do this in physics and maths, okay? Working out the units. Each square bracket indicates mole per dm cube, okay? So that means if I'm working out the units, top part of the fraction is mole per dm cube square. The bottom part is mole per dm cube for the nitrogen. And then for the hydrogen is mole per dm cube to the power of 3. I wouldn't open the bracket at this point yet. You leave that to the very last stage because it's easier to see, right? If I combine them, that means I have, as I said, you may be able to do this straight away, but I'm just showing you if you don't already know how to do it, okay? So mole per dm cube times by 3 lots of mole per dm cube, that is to the power of 4, okay? And they cancel out. 2 lots of mole per dm cube will cancel out with 2 lots of mole per dm cube at the bottom. So I'm left with just 2 mole per, it's so difficult to say this, mole per dm cube to the power of 2 at the bottom. That means my unit is 1 over mole per dm cube square. You can then open the bracket, or you have opened the bracket earlier on just now. Mole square dm minus 6. Okay, I believe this is indices if you are looking at the maths point of view, but I could be wrong. Okay, right, but I can't have a unit of 1 over something. My unit has to be on top. It can't be the denominator of a fraction. So if I bring this up, my unit now becomes mole minus 2. So positive 2 becomes minus 2. dm plus 6, or I could just write it as mole minus 2 dm 6. Okay, so that's how you work out the units. If you want to copy that down, you can pause the video here, I think, because if I zoom out, you wouldn't be able to see this part. Right? So that means the unit for this Kp expression will be mole minus 2 dm 6, or dm 6 mole minus 2. It doesn't matter how you arrange them. The most important thing is the power is the correct value. Okay, so why is there a change in sign? Because I'm bringing them up. So change in sign. Okay, so you can pause here. I don't know if you can see it, but I'll try to zoom in as much as I can. Okay, if you want to pause this here, you can pause it now. And I will move on to the next question. So this is now a system of the formation of hydrogen chloride gas from hydrogen gas and chlorine gas. Okay, so to write down the Kp, it will be the concentration of product, and my product is hydrogen chloride gas raised to the power of 2. That's the stoichiometric number. over the concentration of my products. So the concentration of hydrogen gas to the power of 1, because there's only one mole reacting there, times by, it has to be multiplication, okay? It's not addition. Times by the concentration of chlorine gas, also to the power of 1. Working out units. I'll just show you step by step. Top part, I have mole per dm cube square. I wouldn't open the bracket yet. Bottom part, I have mole per dm cube times by mole per dm cube, and that is the same as mole per dm cube to the power of 2. Okay, so from here you can see that they both cancel out, top and bottom. So what are you left with? No units. And you have to write it in your answer. If there's no units, write it as no units. Okay, so I would just like to highlight again that power comes from the 2 moles of hydrogen chloride gas being produced. Straightforward, yeah? Next example, and the last one, is this system. Now we're no longer in a gas phase. We are now at aqueous. Aqueous is included in KC. Fe2 plus aqueous is also included. Ag solid is not included. Solid, not included. So you cannot just assume that, oh, every question, I will just try to include them in my KC expression, okay? Fe3 plus is aqueous. So that means only 3 out of 4 is included in the Kp expression. Kp is equals to concentration of products, in this case, only one product, over the concentration of reactants. I make it a habit, especially for your notes, to write down the state symbols, okay? Working out units, so that's done. Everything is to 1 mole. Units, top part, I have mole per dm cube. Bottom, I have mole per dm cube square, or if you cannot see that, I will do this, mole per dm cube times mole per dm cube, okay? And then top one cancel with one of the bottom mole per dm cube. So I'm left with 1 over mole per dm cube. And usually units, we don't leave it as 1 over. You bring that up, change the sign, mole minus 1, dm positive 3. Okay, so don't confuse this with mole per dm cube. This is dm cube per mole, and they are different. So units, is mole minus 1 dm cube, or dm cube per mole. Don't get this confused with our mole per dm cube. That's totally not the same. Okay, just a reminder for you to change the sign when you bring it up. Change the sign. And we're done. Okay, we're done for the day. So at the moment, we just learn about writing down the expression, but in the next lesson, we will look at how to calculate them using numbers numerically. Okay, right. As usual, please answer the questionnaire on form after this, and the link to that is in the description box below. All right. Assalamualaikum and thank you.